Get started. So last time we did what? We did started up induction and got a certain distance in it, right? Now I have to also preface this by saying that last lecture was probably, arguably, the most important lecture, and because the concepts there are not very intuitive, so it takes a lot of non-intuitive thinking to actually understand this properly. And so last time what we did was we saw how a changing magnetic field can produce a current, right, and induce electric fields and therefore give us an induced EMF. Now Faraday expressed that in his famous equation that we covered. It's what? Integral of, what's the equation? E dot dl, right? E dot dl equals, basically it equals EMF, right? This equals to negative d phi b dt. This equals to negative d over dt integral open surface of b dot dA, right? So this was Faraday's equation, and he expressed the point I mentioned before in that equation. And for this, what do? We first select a loop, then we attach our famous surfaces to it, right? It has to be an open surface to attach to a closed loop, and any open surface will do. It doesn't have to be a flat surface. It can be anything you want. And we change the magnetic field, varied the magnetic field, and we got EMF, right? And this sign, don't get too hung up on it. I mean, that sign is there for mathematical rigor. And in all reality, what you should be doing is just using Lenz's law to figure out the direction. And that is a lot more easier than remembering to carry over the sign and all that. So today we'll expand on this a lot more. So on Monday, we looked at changing magnetic fields, right? If I look at this equation, it's a time derivative of b dot dA. So in principle, well, not even that. I don't care about the magnetic field per se. I don't even care about the flux by itself. What I care about is how the flux changes with respect to time. So we changed this before, right? So if I were to rewrite this dot product, I get b dA cosine of the angle between them, right? If I integrate this, then I get b a cosine of the angle between them. So in principle, we've already varied this. We changed magnetic field and we got our EMF. We could change the area also and get EMF. We could also change this angle between them and also get an EMF. So that's precisely the cases we'll be looking at today. So again, let's start with the conducting loop. And the magnetic field. So here's my conducting loop, and now I have a magnetic field going out of here like this. Let me use a different pen. So here's my loop. Here's my magnetic field, right? And my dA here would be perpendicular to this, not perpendicular, sorry, perpendicular to the surface. And of course, now I have some surface. I'm just making it a flat surface here. There's an angle between the magnetic field here and my area vector, and I'll call that theta. So what's the flux here through this surface? Well, I know that magnetic field flux equals integral of b dot dA. This integral is open surface, right? So flux here, I have an angle between that and that, so I get integral of b dA times cosine of the angle between them. I integrate this, I get b a cosine of the angle between them. Again, as I mentioned, I don't care about what the flux is. Faraday doesn't care about what the flux is. What we only care about is how the flux changes with respect to time. Right? Now, as I mentioned, we could do this in several ways. We could change the area, we could change the magnetic field, or we can change the angle. So, and again, the way I've defined my flux here, my flux is positive because it's in the similar direction to the area vector. So let's do this first. Let's work on changing the angle first. Actually, should we change the angle? Yeah. So let's change the angle first for this. But basically, if my flux is increasing, what's my EMF going to be? Right? Because it's going to try to oppose it. So if my flux is increasing, my direction of current would be what? Right, clockwise. Right? And again, Lenz's law gives you this direction. So no need to worry about the minus signs and all that later on. So if it's decreasing, then obviously it will go the other direction, and then the EMF will also be in the other direction. So now let's change theta. So how will I change theta? Let's take the same loop. So let's look at the same loop, but what I'm going to do now is, again, so this has dimensions y and x. I have some axis there, and I'm going to rotate this about this way. So I'm rotating that. This has the same surface, and initially it has the same dA vector, same magnetic field going in some direction like this. And I'm going to vary this at some speed omega, right? So this has some angular frequency omega, which is equal to 2 pi over the period. Right? Usually period is given by capital T or tau. But today I'm just going to write it out as, so there's no confusion between that tau or T and Tesla units, which we're using for magnetic field. So this is the angular frequency at which it's rotating. So thinking back to 218, if I look at the angular or equations, I have theta equals theta naught plus omega t, right? It's not accelerating, so we can cancel that term out. And I'm going to say that at time 0, my position starting off, my angle is 0, right? So we can get rid of this term. So what I'll essentially have is theta equals omega t. Okay, so let's look at the flux. I have my theta. I have the flux equation there. So flux equals B A cosine theta. Here's omega t. Right? Now, again, I don't care about the flux. I need the change in flux. So d phi b dt gives me B A omega sine of omega t, and I get a negative sign there from the derivative. Yeah? Now, let's be practical here. We know that this has a negative sign. So I'll just cancel this out and say this is equal to the EMF. Right? And again, this is a function of time. So now, So now if I want to find the induced current on that, I know that I induced is going to be equal to the induced EMF over the resistance of whatever that loop is, and this makes the current a function of time. So I have something like I of t is equal to epsilon t over resistance. So my current is a function of time. My EMF is a function of time. So the current, when I rotate that, is going to be a sinusoidal function, right? So this is going to be BA omega sine omega t over some resistance. So I have this sinusoidal function there. So what kind of current is this? It's an alternating current, AC, right? It's the stuff that comes out of the wall wherever the outlets are. There it is. There's one, right? So, all right. So we'll get back to that in a second, but that's alternating current now. Now, I have that loop, one loop. Let's say I double the number of loops. Well, what do you mean? What do I mean by that, you ask? Well, let's see. So do it better. Right, connected over here. So I have essentially two loops there. Right? It's sort of like a spiral, but a square spiral-ish. Now, what kind of surface would I attach to this? A what? Cube? No. Sort of like that. I mean, remember the trick I told you guys. Now, take whatever surface you visualize, dip it in soap, and pull it out. And whatever, wherever the film sticks, that's essentially the surface you'll have. Same story with the spiral, same story with this. Now, so if you want to think about it, it's basically a closed loop with two windings. Instead of the windings being circular, you have a more rectangular shape here. So again, we have to attach some surface to that. That's mandatory. Faraday demands it. Now, what's going to happen to phi? We discussed this also last time. Right, so my flux, phi b, will double now. Right, so I get twice the EMF if I just have two loops. And if I have 1,000 loops like that, what's my EMF going to be? It's going to be 1,000 times that, right? So, and here, the number of windings can be as large as you want. And I think I mentioned something similar to this. That forms the basis of transformers. Right? So, let's look at an example of this. So, or put some numbers to this. Earth has a magnetic field. What did we say the magnetic field was for the Earth? About half a Gauss, right? So that's about 5 times 10 to the negative 5 Tesla, right? So let's take some, a loop with a lot of windings. Right? This has a lot of windings, and I'm going to give you what that is. This has n equals 42, some random number. I attach this to an ammeter for now. So the radius of this thing, let's say, is 30 centimeters. And therefore, if radius is 30 centimeters, then my area of this loop is going to be 0.28 meters squared. You can check that. magnetic field of the Earth is, as I said, half a Gauss. So this is equal to 5 times 10 to the negative 5th Tesla. And I'm going to say it rotates with a period of 1 second. Right? So basically I'm saying that my tau equals 1 second. So it means that omega, my angular frequency, approximately 6 radians per second. Right? 2 pi and more or less 6, so let's go with that. So what is my EMF going to be as I rotate it? I rotate this at that frequency, so what's my EMF going to be? Well, I know the equation for that. I can calculate it. So my EMF as a function of time is going to be 42 windings times 0.28 meters squared of area times 5 times 10 to the negative 5th Tesla times 6 radians per second, right? And times, I have my sine of 6t. So this coefficient, or amplitude as you can look at it, comes out to be approximately 3.5 millivolts times sine t is what you have here. So it's an alternating EMF with the maximum value of 3.5 volts. So if I was to plot this, right, I have a sinusoidal function. Right, so my maximum value, my amplitude here is 3.5 millivolts. Here's my EMF. This is my time, t. So over here, it completes one oscillation. That's my 1 second here. So this part here, from the beginning to here, is 1 second. So again, I know that my induced EMF is equal to my current that's induced times the resistance, right? Ohm's law. We know that. My induced current here will have the same shape as that because it also will be a sinusoidal function. Right? So the magnitude for this will depend on R. EMF here is independent of the radius, but the current will depend on the resistance. Current will depend on the resistance, but EMF is independent of the resistance here. So suppose I rotate this twice as fast now. So my omega is going to be equal to, I had 6 radians, so it's going to be approximately equal to 12 radians per second. So what's going to happen now? My period, the time it takes to complete one oscillation, will half. Right? So I'll get half a second for the period. And my EMF will also double because I have my EMF. Where's my EMF? Did I erase it? Yeah, I erased it. Damn it. So, well, if you guys look back, to your notes if you're writing, I know my EMF as a function of time equals the magnetic field times the area times omega sine of omega t, right? So I have this omega. So my EMF, my magnitude will also double at this point. So what will my plot over there look like? Well, so if this is 3.5, well, I can't reach that high. So this is 3.5. Let's say 7 is somewhere over here. I'd get something like this over a quarter of the way. Get 7. So this is approximately 7 millivolts. That approximately over there is 7 millivolts, 7. And it'll complete the oscillation in half the time. Right? Now, we rotated this and we got a flux. You can also rotate this in such a way that you don't get any change in flux or any flux at all. For instance, this is actually quite easy to show. If I have some loop, I attach some surface to this, and my magnetic field is coming along this way, and I'm rotating it about this way. Doesn't matter which direction you rotate it. At this point, my magnetic field is always perpendicular to my area vector. So the dot product between those two will be 0. So in a case like this, I don't have any flux. I have nothing of this coming through. So there's a problem that sort of talks about this. Just bear that in mind. Think about what the magnetic field direction is, and what the area direction would be, and what the dot product between those would be. But in a case like that, where I was talking about the Earth's magnetic field interfering with that loop, we don't have that problem because it's not coming in more or less uniformly here. So if I rotate this high enough speed, feasibly, I could just attach a bulb to that and light the bulb up, because it will produce some current. As you guys saw, it has small, but I'm guessing it'll probably produce about 3 to 4 microamperes based on this, assuming normal resistance for the wire. Now, in the United States, does anyone know what the frequency is of the current voltage coming out? 60 hertz. So in the United States, we have 60 hertz, right? And so this means that current through a normal light bulb would become 0 120 times. So if I look at that plot, I have EMF goes to 0, and it starts off with 0 there, and it has another 0 there. So in a span of a second, it'll go to 0 120 times. Does that mean that the light bulb actually turns off 120 times per second? Or that there's no light being produced 120 times a second? No, because you still have the filament in those bulbs that gets hot and that stays hot for a lot longer than the relaxation time for this. So those bulbs, the old bulbs with the filament, the tungsten filament in them, they get hot, so they still glow regardless of what the frequency is. I mean, not regardless, but the frequency that's being produced. But the fluorescent ones, or the newer, more energy efficient ones, those actually do go off and on. But it's such a fast frequency that we can't notice it with our eyes. Even LED lights these days, you can see the same thing. And if you want to look at the LED lights, if you put a polarization filter, actually, we'll get to that in a little bit later, or a couple of weeks later, you can actually see them, turn off and on when you're recording with the camera, because the camera can't keep up with that refresh rate. Or even your screens, LCD screens on your laptops or desktops. If you record it with the camera, you'll see the flicker, right? So that's because the frequency is it's high, but high for us, but not high for the camera. Now, this more or less brings about the idea of dynamos and electric generators. Right? So you guys know what dynamos are, right? So if I have, I'm sure you guys have seen this, those flashlights that you crank with your hand, or the radios that you crank with your hands. It comes in those camping kits or emergency gear, right? That's nothing but a dynamo. You basically have magnetic loops, turn it around, produces a current, and you're able to power it. So basically, there the turbine rotates. I have conducting loops in a magnetic field, and that, according to Faraday, will give us an EMF, and that essentially, as I mentioned last time, is what runs our economy. Now, for that, we have, let's say you have permanent magnets, right? And you rotate conducting loops, windings, in those magnetic fields. The higher your magnetic field, the more your EMF, right? The higher the area of those loops, the higher your EMF. The faster you rotate them, the more EMF you have, right? So because, I think I erased it, but we saw what my EMF is, right? It's equal to negative d phi b dt is equals to area magnetic field, so how I rotate it, times sine of omega t. So we can increase this, I'll get a higher EMF, or we can increase the magnetic field, get a higher EMF. We can increase the speed at which we rotate it, we get a higher EMF. So based on what you're looking for, you can modulate either one of those or all of those and achieve what you need. So as I mentioned, in the United States, we have 60 hertz. What's our maximum voltage here? Close. So what we say is, it's 110 times square root of 2. Right? And that square root of 2 is RMS. We'll get to that again. Should we get to that? I'm not sure if we'll get to that. But right, and we basically say it's 110 volts. In Europe, what's the frequency? 50 hertz. In Europe, we have 50 hertz frequency. And what's their voltage? 220 root 2. Now we have a lot of appliances that are dependent on the frequency. And again, you just can't change the omega for this and increase the current we'll get, because if you do that, we have a lot of our equipment that's geared to a certain voltage. I'll just blow out your TVs and so on. Actually, I'm not sure about the laptop adapters and all that. I think they are compatible mostly with both voltages. But regardless, you don't want to just increase the voltage randomly and blow out things. The frequency is also quite important. There are a lot of things that are tuned to a certain frequency. For instance, one of them is the older generation alarm clocks that you guys plug into the wall. Right? How do they keep time? They know that basically they lose power at 60 hertz, so basically 120 times a second. And based on that, they calibrate it to a second, and they're able to keep time. And it's not just the alarm clocks. You also have the older electric shavers. They also are basically the frequency at which they oscillate. They're also geared to the frequency there. And if you've ever been to Europe and you took your shaver from here, it'll start to bite because the frequency is not as high. So it's because it's not tuned to that. And other things are the older record players, the speed at which they rotate. That's also tuned to the certain frequency. So if you switch them back and forth, either they'll appear to be too slow or too fast, depending on which record player you're bringing from where. But I mean, in today's time, most of those, like you don't use those alarm clocks anymore that plug into the wall, right? They all have an internal battery, and they have some sort of an internal quartz crystal. So most of the wristwatches that you all wear, they're based on quartz, right? That has a certain oscillating frequency, and that's how they keep time in there. I think the best, most accurate one, the highest frequency one, is the cesium ones. So that's the standard used for the atomic clocks now. So even the mechanical watches, though they're not as accurate, they also have an oscillating spring in there that keeps time for it. All right, so we're discussing the currents that come out of the wall. So let's look at power stations. Let's say you have a power station that has about 300 kilovolts, right? To get this voltage, let's say we have a loop that has an area of 1 meter squared, right? And if you're looking at the magnetic field of half a Tesla, which is not really unreasonable for the magnets they use there, frequency, of course, we want to achieve is 60 hertz. Therefore, my omega is approximately 360 radians per second. And for this, my n has to be 1700. Right? You can go home and check that. So if you have 1700 loops with those specifications, we can get the 60 hertz frequency. Now let's write this in terms of power. That's what we're looking at. So what's power? Does anyone remember? What's that? Voltage times current, right? So power is my EMF times current. And Ohm's law says that this is I times R, so I get I squared R. What's the units for power? Watts is equal to joules per second, right? Energy per time. So someone has to do work in order to keep these those rings, those windings, turning. And Texas loves their fossil fuels there. No doubt there. We also have nuclear. Also have coal-powered ones that generate steam. So there are many different ways you can keep those going. So a typical power station produces about 1,000 megawatts of power. Right? That's quite a lot. Now, if you want to think about it, you have a normal 100-watt light bulb, right? So if you have to have one of those hand cranks, one of those dynamo things, you crank it for an hour, so 100 watts, right? That's equal to 100 joules per second. So calculate how long it'll take for you to generate one, or for that to burn 1 megawatt or kilowatt. Megawatt's too much. Kilowatt. And I think a kilowatt hour now is 10 cents or ish, 20 cents, something like that. So it's actually quite cheap considering the amount of work that you would actually have to put in to generate something like that. All right, so far we've looked at changing magnetic fields, right? We looked at changing angles. Now let's look at changing areas. Have you guys been in the foyer on the first floor of this building? You guys have a bunch of physics demonstrations. One of them is a bicycle-looking thing with light bulbs where the seat should be. Right? Same principle here. So you turn that on, start rotating it. You have little coils in the wheel. So once you guys are done here, you should go take a look at that. Well, actually, what might be better is I'll try to get that in here on Friday for a demo. And you have little magnets and you have coils. Right? You turn the pedal, turn the cranks. It's going to change the field. You'll have EMF that's going to be induced, and you can turn those light bulbs on. So what we should actually do, I know Specialized. You guys heard that brand for bicycles? So Specialized bicycles, for a while back, they had a laptop stand or a laptop desk type deal that was powered by pedals. So you basically sit there like you would sit on a normal bicycle and just keep pedaling, and that gives you the power to charge your laptop. I think we should all use that just so we get an appreciation for how much power we burn. All right, so let's go back to our conducting loop. Now, on this side, I'll put a crossbar. So if you want to think about it, this is something like a rail gun for those of you who've used those. So over here, I have some magnetic field coming up, right? I also have my dA in the same direction. The dimensions here is L, and this is X. And let's say that I'm moving this with certain velocity v. Now here, I'm going to say that my B is parallel to my dA. Right, it's in the same direction. So what's my flux going to be? Magnetic flux is equal to integral open surface B dot dA. These two are parallel, so I get B times A. Area for this is X times L, so I get magnetic flux equals Lx times the magnetic field B. Now, again, do I care about the flux? No. What I only care about is how the flux changes with respect to time. Right? So what do I have here? When I look at the change in flux, I have to take the derivative of this. L is a constant, doesn't change. B is a constant, doesn't change. What does change is X. So I get dx dt. And you guys all remember from 218 that dx dt is velocity, right? It's moving at a certain velocity. So this equals to LBV. And this is magnitude of EMF. I mean, I need a negative sign there, but we won't worry about that. So that's the magnitude of my EMF. And that's how we change it. Now let's look at a different view of this. Now, let's take that rod, right? And let's say I have current coming towards me. So if I'm looking at the rod like this, the current's coming towards me. It's coming out like that. Magnetic field is going straight up. Now, think back. What's the Lorentz force for this? Or which direction would my Lorentz force be? For those who don't remember, Lorentz force is equal to the current, the length vector, times our cross product with B. So my L is this way, my B is up, so my force, Lorentz force, would be pointing in this direction. Right? My Lorentz force here is I, L, B. Because I'm saying that my current and my magnetic field are perpendicular to each other, or the direction of the current. Does it make sense? Just took a trip down memory lane to chapter 27, right, with the Lorentz forces. So in fact, what would happen is I would have to pull this in that direction. And to do that, work has to be done going this way. So if I want to pull it this way, that rod over there, give it a certain velocity, I would have to do some work. Right? And in this case, I would have to do some positive work. And work here comes in the form of heat because I have current. Presumably those wires, those conducting loops or conducting elements have some resistance. Therefore, it would dissipate and I would have heat going there. Now, if I wanted to move this in the other direction, what would my Lorentz force be here? Would be switch sides, right? There's another equation for that that shows with the velocity. Right? So then still again I would have to do positive work. So either way, if I'm pushing it out or pulling it in, I would have to do positive work, and there's going to be a current on the element. So basically, there's no free lunch here. Regardless of whether you want to push that in or pull it out, you would still have to do work on that. So you're not getting anything out of there for free. Now let's look at the power for this too. So power, again, we said, well, in this case, power is going to be the force that I pull with dotted with the velocity I achieve. Right? So because they're parallel, it's going to be force times velocity. Because again, these two are in the same direction. If I'm pulling it this way, my velocity is going to be going in the same direction. So those two are in the same direction. So my power here is going to be I, L, B, V, right? And this is going to be equal to my EMF times I. So I can cancel the I out. So therefore, my EMF here is equal to L, B, V. Again, we arrived at the same conclusion we did without using Faraday's law. But we did this using based on the derivation of work. Now, let's switch gears and look at something a bit more interesting. Well, it's a bit more interesting to me. Actually, a lot more interesting to me. Now, let's say I have a solid disk, right? It's a metallic disk, so it's magnetic. And I bring it in the presence of magnetic fields. I have south pole here, north here. So presumably my fields would go something like this. Right? The other way. And here's my disk. And of course, now this is a solid disk, so it automatically has some surface to it. So as I pull this in, there's going to be the flux through the surface is going to be changing, right? So the magnetic flux through here is going to change. Does everyone agree? Right, we can see that? Okay. Now this, when the flux changes, is going to create a current on the disk. And it doesn't look like Faraday likes this very much, right? Because it's gonna change some things. So when I move this in here, I would have, let's say a part of the disk is in that field, I would have a current, and let's say from this, it's going in this direction. So again, it's not easy to precisely determine the direction it flows, but from what I'm seeing, it's going to be clockwise, from above, and it produces a magnetic field that opposes the magnetic field that's here. So the magnetic field here that this is going to produce will be opposing that. Right? So these currents right here, they're called eddy currents. Right? And eddy currents produce heat. You have current in these conducting wires or conducting disks. They're going to produce heat. So let's look at the power again for this. So power is going to be my E times I. So this is going to be I squared R. So it's going to produce some current, and the resistance will slow it down. So when the disk goes through here, it's going to slow down. Right? So basically what it's doing is it's converting the kinetic energy into heat. And it's also called magnetic braking. If you calculate the Lorentz force for this, and it's going through in here, right, and I encourage you guys to go home and do that, you'll see the Lorentz force is to the left. Right? And it's basically the Lorentz force is pushing the disk out. Again, so if I look at the force for that, it's going to be my current length cross B, and it opposes the motion of the disk. So there's an image in your book I encourage you guys to look at. Actually, I can bring it up here. But before I do that, let me show you guys a little demonstration. So here, you'll see that this is a pendulum. If I move it about, it moves around, no problem. Can everyone see this? Okay. So there's no problem here. Now, I take this. Let's say now I drop it. What's going to happen? It'll slow down and stop. If this was heavier, it would have some more oscillation and come down. Right? So this is with one of the loops. Let's look at one that has slits. What's going to be the case with this one? So what's happening here? I have my pendulum. It's going through. This is going to produce some current. I mean, depending on the direction it's going, the direction of the current will change, right? And Lorentz force will effectively work in the opposing direction, and it will slow it down. So in the case of slits, right, I have my slits. The current will still be produced, but it's going to encounter air. Air has a huge resistance, so it's still going to slow down, but not as much. See that? So whereas if I didn't have the field, it would just go about. So let's look at one that has slits but doesn't have. The circuit's not closed off at the bottom. It doesn't get affected. Now, this concept in particular is actually used for a lot of things, and for one of them, maybe some of you guys know of, are those induction cooktops, those induction stoves. So how does it work? So induction, you have basically within the stove top. If you ever open them up, you'll see a gigantic coil. It's getting current from the wall. So it has an alternating current, therefore the coil will produce an alternating magnetic field. Right? And you put whatever container on top, metallic, and for it to work best, it has to be something that's magnetic. So basically, if you can stick a magnet to the surface or to that metal, then it will work with the induction cooktops. So the magnetic field will create eddy currents on that surface, and they'll get dissipated as heat, and that's how it heats up. Same concept in that, same concept in my new induction rice cooker. It's even the same concept that's used by trains to brake. So you guys have all heard of the bullet trains, right? More or less. So you have the TGV Express in Europe, you have the Shinkansen in Japan, Germany has their own, you have China also has some. And what they use for in Shinkansen is basically creates a magnetic field. Those create eddy currents, and they cause the train to brake. Another cool thing about those bullet trains is, well, the TGV not so much, but the Shinkansen, they are partially levitated. Shinkansen actually has rubber rollers to propel them along, but they're not completely levitated. But if you guys ever go to China, the new trains in Shanghai, they're fully levitated, those trains. That's pretty cool and quite efficient too. And I'm from the civilized part of the country in California, and they're actually constructing a high-speed rail network from northern to southern California, because a lot of people that commute from down there. So they're constructing that network, and hopefully once I'm done here and I move back, the train system will be completed. And I think last I heard they were actually looking into a German company that's going to produce completely levitated trains. That's something to look forward to. All right, let's take a quick 5-minute break, and we'll start on a new topic. let's move on to displacement currents. Now, I mentioned last time, the previous time, that Ampere was incomplete, or Ampere's law was incomplete. I'm not sure about Ampere as a person, but his law was incomplete. So let's take a closer look at Ampere's law. So what I have, let's start with a capacitor, a parallel plate capacitor. All right, so something like that, something like this. I have current moving about in that direction, which means that I have an electric field that's produced that goes about like that. Now the electric field for this is given by, well, I have some charge density, sigma. This is charge density over kappa epsilon naught. This is going to be equal to the charge that's free over the area of the plates times kappa epsilon naught. So let's assume that these are circular plates of radius r, which gives me an area of over pi r squared kappa epsilon naught. So this charge is building up all this time. Now, if I want current, well, that's simple. Current, I know, is dq free over dt. Right? And so from here, I can conclude that my change in electric field is going to be equal to I over pi r squared kappa epsilon naught. Only if there's no current will there be no charging, and there will be no changing electric field here. Only if there's no current coming through. Now, since we're looking at Ampere's law, I guess the intelligent question is, how does this affect the magnetic field? Well, let's take a couple points here. Let's start off with this point over here, point P, right? P1. Now let's have a second point somewhere over here, P2. So P1 is far away from the surface, so it's hard to believe that Ampere won't give us the right answer. So if I'm looking at the magnetic field here, I attach my loop, I attach my open surface to this, right? Flat open surface here, and I'll go about trying to calculate it. Now, how can we calculate the magnetic field at both P1 and P2? So now that there's an opening here, how is that going to affect it? Well, to calculate the field there, in principle, I could do it with BS of R. In principle, it is possible. But then because the current would diverge like that, I don't know quite how to approach it with BS of R. Well, how about Ampere? Let's try with Ampere first. So I have my P1 there. I attach my surface. And so what's Ampere going to give me? I have B times the area. The area? No, the circumference of the loop. That's going to give me 2 pi r. And that's going to be equal to mu naught I enclosed, or penetrating. And here I can say B is equal to mu naught I over 2 pi r. That answer is as expected. We've done this before. Everything is good. Now, let's look at the magnetic field over here. So I attach my surface to this here. Well, there's no current penetrating through that surface, right? There's no current enclosed. So Ampere's law will say that the magnetic field over here is equal to 0, which is absurd because we know that there has to be a magnetic field there. So let's make this a little bit worse. Let's take the same surface or the same configuration, and let's change the surface a little bit. So I have my capacitor, I have that, I have my point P1, right? Here's my loop, here's my current flowing in. Now, Over there I picked a flat surface, but remember I said you don't have to pick a flat surface, you can pick any surface you want, right? So what if my surface I'm looking at is something like this? And I'm calculating the magnetic field there. Over here again, I'll get B equals 0 because there isn't actually any current flowing through, right? So as of now, Ampere's law is quite inadequate. It doesn't hold up. So Faraday and Ampere were both aware of this shortcoming, but it was actually Maxwell who fixed this and argued that when you have a closed loop and surface, any surface you pick has to give you the same answer, which is quite true. So what is so special about these capacitor plates here? Well, we know that because there's a current going in, we have a changing electric field. And so Maxwell thought, well, we know from Faraday's law that a changing magnetic flux will give you an electric field, right? So he thought maybe, just maybe, a changing electric flux can lead to a magnetic field. And as a recap, for those of you who don't remember, our electric flux, the definition is quite similar to the magnetic flux. So my electric flux is defined as open surface integral of E dot dA. If it's closed surface, then it becomes Gauss's law. That's different. Yes, I did. Sorry, thank you. Well, so he concluded that this term has to be added into Ampere's law to make it kosher again. Well, not again, but to make it kosher. So from here, as Maxwell suggested, let's add the term. So we know Ampere's law is integral closed loop of B dot dl. This equals to mu naught I plus, I have my epsilon naught kappa and times that dt of the electric flux, so it's d over dt of the integral of E dot dA. And this is my open surface. And this particular term right here was called displacement current. So now that we've completed this, can we open up the champagne bottles and start partying? We're done with Maxwell's equations? No, we can't, because we still need to go back later and make a little adjustment to that term. It's a tiny adjustment, but still, nonetheless, adjustment has to be made. So let's hold off on the partying for now. Once we're done, we effectively now can start partying. So let's try this. So let's again try to calculate the magnetic field over here at point P1 due to that. Well, we have everything is assumed the same. That's my surface, P1. Everything is the same as before. When I go through Ampere's law, I get B times 2 pi r equals mu naught some current I is going through. But then there's no electric flux over here at this surface. So that displacement current term is 0. So this holds up. So I get B equals mu naught I over 2 pi r. We're good. No problem there. So we got the same answer as before. Now let's look at that surface over there. So where we have our surface that goes through that plate. Well, the left-hand side of the equation will again still give me B times 2 pi r. This is going to be equal to, we know that there's no current that's penetrating through it, so that term is 0. So what we're going to be left with is mu naught epsilon naught kappa d phi E dt. And again, so one key thing we have to assume is that there are no fringe fields. So what fringe fields are is, you have a field that seeps through from the sides. We're assuming it's one of those super idealized conductors, no fringe fields, nothing, which in reality doesn't exist, but that's the cool thing about physics, right? Have you guys ever heard the spherical cow joke? No? All right, well, we got time for a joke. So it's Texas, they're farms, and you have a farmer calls up a veterinarian, a biologist, mathematician, and a physicist because this cow is sick. Right? So the veterinarian goes in, couldn't figure it out. The biologist goes in, does his examinations, couldn't figure it out. Mathematician goes in, does his examinations, couldn't figure it out. The physicist goes in, does his examination, does some calculations, comes out and says, I know why your cow is sick, I know how to fix it, but my solution will only work on a spherical cow in space, in a vacuum. Because that's the idealized condition we're looking at. You're looking at a perfect sphere in a vacuum, so none of the dielectrics or anything else applies. That's what physics we're essentially looking at. All right, but again, we're assuming no fringe fields, so my flux here is going to be E dot A, right? So this is going to be pi r squared, pi r squared times E. Now d phi dt is equal to dE over dt times pi r squared. Now, to get what dE dt is, we know that my current, my displacement current, is given by epsilon d phi E dt, right? And I know that my current density, J, or in this case, we're going to look at capitals, my displacement current density is basically that divided by the area, right? So this, if I divide by area, I would get phi E times A. A is a constant, so if I divide that by area, I would just get simply epsilon dE over dt. Right? So now that we've done that, so once I apply Ampere's law, I get B dot 2 pi r equals mu naught epsilon naught kappa d phi E dt. Right? So this is the same. So this gives me mu naught epsilon naught kappa. That's going to give me I have times the area, so I have pi r squared times the d dt term. That's going to be I over pi r squared kappa epsilon naught. So pi r squares cancel out, kappa epsilon naught goes away. So, and again, this is the area. So what I end up with here is mu naught I. Right? So from here, again, I have B equals mu naught I over 2 pi r. Again, so Maxwell predicted correctly, and hooray for Mr. Maxwell now. Now, let's go a step further and calculate the magnetic field at any point. So we calculated at a certain radii r there. So if I have my parallel plate capacitors, some point r here, looking at the surface there, right? And this here is r. What I would get here is same thing. So I get B times 2 pi small r. Right? That's a given on the left side. On the right side, I have times mu naught epsilon naught kappa pi r squared I over pi r squared epsilon naught kappa. So this r is the radius of that disk. So pi's cancel out, epsilon naught kappa cancels out. So I get here my magnetic field to be small r times I times mu naught over 2 pi big R squared. So if this is below that those plates. So if I was to plot this, right? So for the first stint, when it's below the plate radius, it's increasing as a function of R, right? It's proportional to R. So what I would get here, I would get some increase until it hits R. And then once it hits R, once it's beyond that, then that field comes into play. And that falls off as 1 over R. So I would get something like this. That's my magnetic field as a function of radius. Right? Again, so this is not quite as pointy. It's actually not true. I mean, it's true for idealized case here we're looking at, but in reality, this is not quite so nice because of the fringe fields that I discussed. So when Maxwell introduced his displacement current terms, the ID term there, he actually predicted radio waves exist. He even calculated what their speed would be. He calculated that the speed would be the speed of light, c. And in 1879, that's when that's the year Maxwell died. I think he was about 48 when he died. It's pretty young. A German physicist, Helmholtz, you guys all heard of Helmholtz, right? Helmholtz coil. He asked his student at the time, who was 22 years old, Hertz. He asked Hertz to try and demonstrate that Maxwell was right, that radio waves do exist. And at that time, Hertz declined. He said, there's not the equipment I need in existence to be able to do this effectively. But 7 years later, the equipment had been invented, and Hertz took up the challenge, and he showed it. He showed that what Maxwell indeed said about radio waves' existence was correct. Hertz died 5 years after that. I think he was 37, so yeah, he was 37 years old when he died. Again, pretty young. So had he actually lived 10 years longer, he would have been probably awarded the first Nobel Prize in Physics in 1901. So that because they didn't give out Nobel Prizes before then, he didn't get it. So why did Maxwell call that term displacement current? Well, in the presence of a dielectric, the changing electric field will indeed cause a current between those plates. And what Maxwell believed it to be was, vacuum was just a special case of a dielectric, where a dielectric constant is 1. I mean, he was sort of right, but the polarization of the plates changes all the time, so you can't get a rearrangement and say that the current, but we do know that the current exists there. But in a vacuum, there's no current. Maxwell thought there'd be current there in a vacuum, but in a vacuum, we won't have current between those plates. But again, doesn't matter, right? What's in a name? We call it displacement current, doesn't matter. As Shakespeare once famously said, a rose by neither name will smell just as sweet. So, name doesn't matter. So that effectively concludes displacement currents, and I believe that concludes chapter 29. It does include superconductivity and other stuff in 29, although I wish I can get to superconductivity because that's sort of my area of expertise or my area of research. We won't have time to do that. We won't have time to get to that or magnetic materials, which, again, I wish we did. Also alternating current, which I wish we did, but we don't have time to cover all that. Other than that, have a good Thursday, and I'll see you guys on Friday.